picked out of the same portion or picked out of different portions of the same magnitude are brought together, are we able to tell the magnitude of their sum? That is, can we tell how big or how small the combination of those portions can be? That takes us to lesson objective number 6. That is addition and subtraction of vulgar fractions. Please follow me as I develop it. Pay attention to all details in this section. With it, you may be able to understand what is hanging onto it. Again, it is addition and subtraction of vulgar fractions. In this section, we seek to learn addition and subtraction of vulgar fractions. Notice that I said vulgar fractions. What it means is that in adding and subtracting fractions, we're going to concentrate on only vulgar fractions. Perhaps some other time we can concentrate on adding and subtracting decimal fractions. Before we proceed, let me remind you that there is a case we did not handle at the outset of this topic. Recall what happened. I remember, and you should remember too, that this question remained unsolved. One orange was broken into 3, and one portion picked out of it, named 1/3, was added to another portion, which was gotten this way. Another orange was broken into 5. The orange of the same size broken into 5 portions, and 2 picked out of the 5. The person that picked 1 out of 3 portions had 1/3 as his own share. And the person that picked 2/5 had 2 out of 5 portions as his own share. Now, what if the two persons pull their shares together? That is 1/3 plus 2/5. Recall that this has been a question that has been hanging around our neck. It was suspended at a time like this. Let me tell you that the time has come in this section for us to learn how to get an answer to this foregoing question. Again, it is 1/3 plus 2/5. I hope you want to know how to get an answer to this question and to this problem and similar problems. I'm afraid that we are still going to further suspend this until shortly afterwards. Why? It is challenging to add this to this, especially because this one was picked out of 3 portions of 1 orange, and these 2 were picked out of 5 portions of a different orange. That means even if the 2 oranges have the same size, how can you add 1 out of 3 portions to 2 out of 5 portions? That sounds challenging, right? Okay, before we come back to it, let us first of all learn how to add 2 fractions, which were picked from the same number of portions. That takes me to 1/3 plus 1/3. Please see it. And here it comes. This, while being suspended, will take us to this one. 1/3 plus 1/3. I hope you can imagine what we're doing here. From 1 orange broken into 3, somebody took 1 from it. We still have more portions out of it to pick from. Another person picked another 1 from the same 3 portions. The 2 persons now have each 1/3. That means the first person has a share of 1/3, and second person has a share of 1/3. What if the 2 persons pull their shares together? It is also possible that it is somebody who picked first 1/3 and was told to pick another 1, and he picked again 1 out of the 3. If he puts together the total of what he has picked, what will you say he has picked? Logically, we conclude that what the person has picked is 2 out of 3 portions. Just imagine that. Something broken into 3. You pick one, pick another one from the same 3 portions, and somebody is asking you, how many portions out of 3 have you picked? The answer is that you have picked 2 out of 3. This is how 1/3 plus 1/3 became 2/3. That is easy enough. You agree with me? Now, let us consider another case, and therefrom, along with this one already considered, draw some conclusions that will lead us to making a law or producing a law of adding and subtracting fractions that possess the same denominator. Please see another example. And now you have it. 1/5 plus 1/5 plus 1/5. What will it be? While you are thinking about the answer, let me again remind you that this could be that one orange was broken into 5. You pick 1 out of the 5, and you have 1/5. Pick another one, you still have another 1/5. And yet pick another one to have 1/5. That means you picked 1 out of the 5, picked another one out of the 5, another one out of the 5. Now, if you are told to tell how many you have picked out of the 5, what will you say it is? Let me tell you. In fact, there is no need to argue that the answer is 3/5. Because of simple reasoning, all of us should conclude that the answer to this number operation is 3/5. We can as well choose other ones that will highlight the importance of picking from the same number of portions and checking altogether how many that have been picked. That is not the only thing we can do. Sometimes we can do subtraction with the number of portions picked from the same pool of portions. Let's see just one example of such cases. And this is yet another example. 4/5 minus 1/5. What do you think the result will be? While you are thinking, let me illustrate or interpret what has happened here or what is happening. That same orange that was broken into 5 was to be shared among people, and somebody picked 4 out of those 5, or 4 persons picked 4 portions out of the 5. Whichever way, whether it is one person that picked all the 4 out of 5, or 4 different persons that pulled their shares together, the result is 4/5. The message is that 4 portions have been picked out of the 5. We now say minus 1/5. What does this mean? It means if one person is holding 4 portions out of 5, and he decides to give away 1 out of those 4 portions, what do you say will be the description of that one he wants to give out? I repeat, somebody is holding 4 out of 5 portions of one orange, and he wants to give away or give out 1 out of the 4 portions. How do you describe that one he wants to give out? It is still 1/5. Because that one he wants to give away was picked from 5. That means it is not going to be ordinary 1, but 1 picked out of 5. That takes us to 4/5 minus 1/5. Please, when the person has given away 1 out of these 4, what do you think is going to remain with him? Your answer, perhaps you've got it, but compare it with what comes next. Please watch. Inarguably, the result is 3/5. is 1 over 5, or 1 out of these portions taken, what remains will be 3 out of 5. So the result is 3 over 5. Now, look at these 3 examples. What each of them is and how the answers turned out to be what they are. What is common to all the 3 number operations? This number operation, this number operation, this number operation. The answers may be different or the same, but we concentrate on the number operations. That is 1 over 3 plus 1 over 3. 1 over 5 plus 1 over 5 plus 1 over 5. 4 over 5 minus 1 over 5. What have you observed that is common to all of them? One striking common thing that we find among the 3 examples is that the 3 of them, all the 3 examples or the 3 number operations, possess the same type of denominator. In the first number operation, 3 is here and 3 is here. That means that both fractions possess the same denominator. In this second operation, all the 3 fractions possess the same denominator. What is it? 5. In the third number operation, the 2 fractions possess the same denominator. What is it? 5. Could it be why it was easy for us to get the answer straight like that? Certainly, yes. That is even why it was difficult for us to get the answer to this first one. The challenge we had in this first one is that 3 is here and 5 is here. Because of that, we could not get the correct answer. Later, we get back to it, and that will be after making a law out of this first sort of addition and subtraction of fractions that possess the same denominator. How do we generate a law of adding 2 or more fractions that possess the same denominator? It is by observing what happened in each case. In all these 3 cases, something happened. Watch it. 1 plus 1 gave us 2. These 3, only 1 was picked. See it here. Also here, 1 plus 1 plus 1 gave us this 3. Only 1 out of these 5, out of these 3 5s, picked to become the denominator of this answer. That is 5 here. 4 minus 1 is equal to 3. And this common denominator, which is 5, was picked to become what it is here. With this in mind, a kind of consistency is developing, and consequently, a law will come out of that consistency. Now, what do you think is the general statement, symbolically speaking, about adding and subtracting fractions that possess the same denominator? Whether there are 2 fractions or more, what law do you think summarizes the addition and subtraction of fractions that possess the same denominator? While you are thinking, see a law on the board and compare it with what you were thinking. Right, this is a law of adding and subtracting fractions that have the same denominator. It says A over E plus or minus B over E plus or minus C over E plus or minus D over E plus or minus any other fractions that possess the same E as the denominator. The result will be by adding these numerators, A plus or minus B. It might be adding or subtracting as the case may be, so it is not just adding. That is why we have A plus or minus B plus or minus C plus or minus D plus or minus other numerators. See it here, all over the same denominator. I hope this law makes sense to you, and you also know that it summarizes these 3 number operations. Notice that this first one is addition of fractions. This second is also addition of fractions. The third one, of course, is that of subtraction of fractions. And yet, the same procedure is involved. The same observation was made from each of the three number operations. That is why the same conclusion was reached for all the three. So anytime you see any two or more fractions to be added or subtracted and they possess the same denominator, the answer can be gotten in this straightforward way as you are seeing it on the screen. Now, let us see more examples of adding and subtracting fractions that possess the same denominator. And now, the examples are here. The first one says 3 over 7 plus 1 over 7. Notice that they have the same denominator. So what do? What they call this law. The law states that we just have to add the numerators and then use the sum of the numerators as the numerator of the new fraction that will result from the addition. That is talking about just this first one, because in other cases we can do subtraction as we'll see in example 2 later. Now back to this one, 3 over 7 plus 1 over 7 will just equal to 3 plus 1. That is this 3 plus 1 over 7. See it here, 3 plus 1 is 4. So in the end we have 4 over 7. I hope you can see how this law came to apply here and that the correct answer is what we have here, 4 over 7. What about second example? We have this 5 over 6 minus 1 over 6. What will the answer be? This one is subtraction, pure subtraction, but it conforms to this law. Why? Because this law shows that no matter what we have as numerators, they all possess one denominator. And this is like that. Though we have 5 and 1 here, we have 6, the same denominator. So this law will be used to evaluate this number operation. Let us do it. How? Are we going to add 5 to 1 or subtract 1 from 5? It is the sign between them that tells us. Don't forget that this sign says it is either plus or minus, depending on which one exists between them. Here, what exists between 5 over 6 and 1 over 6 is minus. That is why we're going to subtract. That is why this minus is here. So 5 minus 1 is 4. Then pick 6 as a common denominator. See it here. So 5 minus 1, 4, then over 6. 4 over 6 is the answer. But we don't like leaving a fraction in this form, in a form which is not in this lowest term. 4 over 6 can be broken further into 2 over 3. I hope you know how 4 over 6 became 2 over 3. All right, the last answer is composed of both addition and subtraction, but it also conforms to the structure that will make us apply this law. What is it? E simply means that whatever the value of E is, the same thing applies everywhere below. See, in this case, our E is the 8. 8 here, 8 here, 8 here. That means that this law will apply. The numbers, which are numerators, A, B, C, D, and more, depending on how many fractions we have, may be different. But as long as they have the same denominator, this law will be used. And that is why this will be evaluated with this law in mind. What do? Just carry out number operations with the numerators. 5 plus 1 minus 3. See it here. I hope you know why this plus is here and why the minus is here. By now, you should have known that. And then pick one of these 8s as a common denominator. Don't forget that this law was based on consistent observation made from 3 numerical experiments with fractions that possessed the same denominator. Now the answer is equal to 3 over 8. Why? 5 plus 1 is 6. 6 minus 3 is 3. So 3 over 8 is the answer. Now, watch out for an exercise. Evaluate each of the following operations. The first one says 2 over 9 plus 1 over 9 plus 4 over 9. Please remember that law that is used in adding and subtracting fractions that possess the same denominator. Number 2 says 5 over 7 plus 1 over 7 plus minus 4 over 7. Number 3 says 1 over 2 plus 1 over 2 plus 1 over 2. Something will happen that I've not spoken of when you get the answer to this number 3. When you get the answer, find out what new thing has happened. Now, let us go back to fractions having different denominators. Recall that this fraction has been a foregoing fraction, 1 over 3, and this has also been a foregoing fraction, 2 over 5. And this case is a foregoing case. At this point, the time has come for us to find an answer to 1 over 3 plus 2 over 5. This, in a way, is different from the questions we have solved. Why? If you watch this number operation, 1 over 3 plus 2 over 5, you notice that, unlike others, this case has two different denominators, 3 and 5. In the former cases, we had situations in which what is here is what is here. In this case, we have 3 and 5. So this is a special case of addition of fractions. Now the question, what is the answer to this addition of two fractions? The only way to get the answer is to ensure that both of them, both 1 over 3 and 2 over 5, come to possess the same denominator. Fundamentally, it is quite challenging to just come and add 1 over 3 to 2 over 5 and get the accurate answer. One portion was picked out of 3 portions of orange. If the same orange had been broken into 5 and 2 picked, you can't expect 1 picked out of 3 portions added to 2 picked out of 5 portions to give us a straightforward answer. To make it possible to add 1 over 3 to 2 over 5, we should ensure that we reconstruct this 1 over 3 and 2 over 5 to new fractions that will possess the same denominator. What exactly is required in making sure that 3 and 5 are made to have the same denominator or to become the same denominator? All right. One that should come into your mind is that 3 has multiples and 5 has multiples. Please follow me as I list the multiples of 3 and afterwards multiples of 5. With their multiples, we can make a headway. Please watch out. And here they come. The multiples of 3 are 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. I hope you know what I mean by multiples. That is, if we keep on adding 3 to 3 each time, the numbers we get as we keep adding 3 are the things referred to as multiples of 3. For instance, after 3, if you add 3 to 8, what you have is 6. After that, you add 3 to this 6, what you have is this 9. plus 3 again is this 12, plus 3 again is this 15, that way until 30. So the numbers we get as we keep on multiplying 3, that is, as we keep on repeatedly adding 3, are the things referred to as multiples of 3. Similar truth applies to the multiples of 5. You can see 5, 10, 15, 20, 25, 30. I hope you know how we got these multiples of 5. Just the same way we got multiples of 3 by adding 3 each time. We got the multiples of 5 by adding 5 each time. What it means is that 3 into a number of times will give us 6. 3 into a number of times will give us this 9. 3 into a number of times will give us this 12. Yes, we know that 3 times 2 is this. 3 times 3 is this one. 3 times 4 is this. 3 times 5 is this. 3 times 6 is this. In that order. Likewise, 5 times 2 is 10. 5 times 3 is 15. 5 times 4 is this 20. 5 times 5 is 25. 5 times 6 is this 30. It does not mean that multiples of 5 stop at 30 and that multiples of 3 stop at 30. For convenience, I just want to stop at 30 for each of them. Now, can this tree experience an upgrade? That is, can this tree jump to something higher than 3 but a multiple of 3? Can this 5 jump to something higher than 5 but a multiple of 5? Yes. Please. How is it possible? If I want to make this 3 become 6, I will just multiply up and down by 2 to make it become 2 over 6. If I want to make this 3 become 9, I'll just multiply up and down by 3. That is 1 times 3, 3. 3 times 3, 9, to give us 3 over 9. If I want this 3 to become 12, what will I multiply up and down with? Is it not 4? Surely, if I multiply 1 and 3 by 4, I will be having 4 over 12. What if I want this 3 to be 30? Obviously, I will multiply up and down by 10, so that I will have 10 over 30. And don't forget that whenever the numerator and denominator of a fraction are multiplied by the same number, a new fraction is created, and that new one has the same value as the former one. So multiplying 1 and 3 by a chosen constant does not change its value. It only changes its appearance. Similar thing could be said of this 2 over 5. Can I make this 5 become 10? Yes. How? I choose 2 to multiply both 2 and 5. That will be equal to 4 over 10. If I want to make this 5 become 15, I can also do it. How? I will choose 3 to multiply 2 and 5, and that will become 6 over 15. What if I want to make this 5 become 20? I will choose 4 to multiply up and down, and that will give us 8 over 20. What if I want to make this 5 become 30? I will choose 6 to multiply up and down, and that will give us 12 over 30. All these fractions I appear to have gotten by these multiplications are equal in value to 2 over 5, but only might look different. Don't forget that two fractions might look different but have the same value. Again, when the numerator and denominator of a given fraction are multiplied or divided by the same number, a new fraction is born, and that new fraction has the same value as the fraction it is coming from. We're going to exploit this property of fractions to ensure that we change each of these two fractions to different forms that have the same value with them. How? Please watch out. Now look at what has come. I have been able to solve this number operation in two ways. Let me explain each of the two ways. Before I go headlong into it, notice that in the outline of multiples of 3 and the outline of multiples of 5, we have multiples which are common to both of them. Please carefully watch again this array of multiples of 3 and this array of multiples of 5. Did you find any multiple that is common to both of them? Is it just one number common to them, or none, or 2? Certainly, I'm seeing 2. Notice that in this array of multiples, 15 is in 8. 15 is also in this second array of multiples. It therefore means that 15 is common to multiples of 3 and 5. As a result, we call this 15 common multiple, or just CM. Do we have any other CM? That is, do we have any other common multiple? Yes. Watch again. 30 is here and 30 is here. That means that 30 is a second common multiple. If we keep listing the multiples of 3 beyond 30 and multiples of 5 beyond 30, we will still get other higher common multiples. But for simplicity, like I said earlier, I had to end the arrangement of the array as 30. Let's just make do with 30 to avoid complications. Now, so far we have been able to isolate two numbers, 15 and 30, as multiples common to 3 and 5. The implication is that somehow something multiplies 3 to give us this 15. Also, something multiplies this 5 to give us 15. That means that we can upgrade this 3 to 15 simply by multiplying it by something. We can also upgrade this 5 to 15 by multiplying it by something. Now we ask ourselves, what is that that multiplies this 3 to make it 15? It is 5. Now, and what is that that multiplies this 5 to make it 15? It is 3. Therefore, we can actually upgrade this 1 over 3 to something over 15. We can also upgrade this 2 over 5 to something over 15. I mean, we can upgrade this 3 to 15 and this 5 to 15. How is it done? Notice the way it was done in this second line of action, this place. Remember that when the same number multiplies up and down, a new fraction is born or is created, but that new fraction has the same value with the former fraction. Don't forget that I want to choose a number to multiply up and down with so that this 3 becomes 15. Why am I insisting on 15? It is because 15 is common to multiples of 3 and multiples of 5. Now back to the process. So you now know why I chose 15 for 3 and 5. It is because 15 is a common multiple to 3 and 5. So I want to make this 3 become 15 and make 5 become 15. Now, how do I make this 3 become 15? Obviously, that same 1 over 3 is here, but I'll multiply up and down by 5. 3 times 5 will give us 15. 1 times 5 will still give us 5. Then, what about this one? What do I do to make this 5 become 15? 2 over 5 is still here, as it is here, but something new is happening to it. up and down, I multiplied by 3. Why? So that 5 times 3 becomes this 15, which is written here. At this point, I hope you now know why we insisted on upgrading 3 and 5 to 15. We couldn't have reasonably insisted on pushing 3 and 5 to 12. The reason is that 3 and 5 cannot simultaneously jump to 12. The only way 3 and 5 can do that is by use of non-whole numbers, which in this case is not feasible. So we insist on using whole numbers to upgrade denominators to higher numbers, which in this case are called common multiples. Now let's make progress. I now think that you understand what has gone on here. All right, and we now know how 1 times 5 over 3 times 5 became 1 times 5 over 15, and how 2 times 3 over 5 times 3 became 2 times 3 over 15. Now, let's make progress. Simplify by saying 1 times 5 is 5. 15 is still there, see it here. So the whole of this has become this 5 over 15. And the whole of this has become 6 over 15. Why? 2 times 3 is 6, then over 15. That will give us 6 over 15. That means that these two fractions have become these two fractions, meaning that this is equivalent to this, while this is equivalent to this. Adding these two fractions is just the same thing as adding those two fractions. Now, which of these two is easier to add? Anyway, recall that the reason why this whole process is going on is that we have been trying to avoid one thing. We have been trying to avoid the difficulty of adding two fractions that do not possess the same denominator. Therefore, I repeat, adding 1 over 3 to 2 over 5 is the same thing as adding 5 over 15 to 6 over 15. Any answer you get at last is the answer to any of these two number operations. But adding 1 over 3 to 2 over 5 is difficult, while adding 5 over 15 to 6 over 15 is easy. Why? It is because before now, we learned that it is easy enough to add fractions that possess the same denominator. Let me explain or remind you with this number operation, current number operation. I want to explain why it is easier to add this to this than this to this, though the two of them are equivalent. Let's assume that one orange was brought and then broken into 15 equal portions. One person chose 5 from those 15. From the same 15 portions, another person took 6 portions. If the two persons pull their shares together, or if both portions or sets of portions have been picked by the same person, if he puts together the two portions he had picked, or the two sets of portions he had picked together, if he puts the two sets of portions he has picked together, what exactly will be the total? Remember, 5 picked out of 15 plus 6 picked out of the same 15. Simply, as we had been taught earlier, the answer to this would simply be adding this 5 to 6, since they were picked from the same number of portions. 5 plus 6 is 11. That means altogether there are 11 portions already picked out of the existing 15 portions of one orange. As a result, this is the answer to this number operation. That means that 1 over 3 plus 2 over 5 is equal to 11 over 15. All right, let us try to solve it another way. This time around, we're going to choose 30 as their common multiple. That is, earlier we chose 15 as the common multiple, but this time around we're going to choose 30 as the common multiple, a multiple common to 3 and 5. Now watch out. That means that we can convert this 3 to 30 and convert this 5 to 30. How do I convert this 3 to 30? I'll multiply it by 10. Not just 3 by 10. If this fraction must maintain the same value, that 10 that multiplies 3 must multiply 1 also. That means we multiply up and down by the same number. See where 10 is multiplying up and down. So we have 1 times 10 over 3 times 10, giving us 1 times 10 over 30, and that is equal to 10 over 30. What about this 2 over 5? I also want to push this 5 to 30. How is it done? We multiply it by 6. To make the result of this multiplication equivalent to this one, we multiply both up and down by that same 6. That is why we multiply 2 and 5 by the same 6. See the procedure here. The same 6 multiplied 2 and 5 to give us this 2 times 6 over 30, because 5 times 6 is this 30. And then 2 times 6 is 12. That means that altogether we have 12 over 30. It therefore means that 1 over 3 plus 2 over 5 has become 10 over 30 plus 12 over 30. That means that both 3 and 5 have now become 30 each. The reason is that we want to make it possible to add the two fractions, since it is practically difficult to add these two fractions in this form. Again, why is it easier that we add these two than it is to add these two? It is because 10 picked out of 30 added to 12 picked out of the same 30 is much easier. If you pull 10 together with this 12, you have 22 picked out of 30. Therefore, the answer to this number operation is 22 over 30. But we can still bring this fraction down to its lowest term. How is it done? Divide both up and down by 2. That will lead us to 11 over 15. The same answer we got earlier. I hope that what has gone on here is clear to you. From these two approaches adopted for solving these two number operations, I can derive two formulas that will be used in adding and subtracting fractions that possess different denominators. I want to assure you that if you repeat this same process with subtraction, what is applicable here will also be applicable in that case. I challenge you to bring up other examples of fractions possessing different denominators. Carry out subtraction between them and use this same method. You will see that the answer you're going to get is correct. Therefore, I want to show you that this process works for both addition and subtraction. Again, I said that it is possible for us to get formulas from these two procedures. Formula for adding two or more fractions that possess different denominators. Please follow me as I argue out formulas that will help us add two or more fractions that possess different denominators. Now let us look at the first formula. We just have to recall from the recent exercise that 1 over 3 plus 2 over 5 was given as 5 over 15 plus 6 over 15. I just hope you remember. And how was this 11 over 15 gotten from here? Remember, we just added 5 to 6 to produce this 11. That is why here the result before this last one is 5 plus 6 all over 15. So far, I hope you now remember how this became this, and how this became this, and how this became this. This is the last answer, the final answer, but it was gotten from here. What it meant is that this number operation produced this result, and this result. That means that this number operation produced 1, 2, 3 results. Each of them is correct. To help us bring out a formula for adding and subtracting fractions that possess different denominators, especially when there are only 2 fractions involved, permit me to equate this number operation to any of these 3 results. I want to equate this number operation to this. That is why the summary has it that 1 over 3 plus 2 over 5 is equal to 5 plus 6 all over 15. I hope you know that this is one of the summaries we can derive from this long statement from here to this point. All right, let's make progress. At this point, let us concentrate, having known that this is correct, on this final result. 1 over 3 plus 2 over 5 is equal to 5 plus 6 over 15. Let us find out how this 5 came to be. If we watch this number operation and watch this answer, and we see a way of obtaining this 5 from this number operation, and this 6 from that same number operation, and this 15 from the same number operation, and test it again with other similar number operations. If we see consistency in the observation we're going to make therefrom, from that observation, we make a conclusion, which happens to be a law of adding and subtracting fractions, especially 2 fractions possessing different denominators. Please follow me as I make observations between this number operation and this result. And here comes the observation. This summary is repeated here. In 1 over 3 plus 2 over 5 is equal to 5 plus 6 over 15. That is, if this is number operation, and this is how to get the answer. How do you think this 5 came from this number operation? If you watch this number operation, it is as if this 5 here was gotten by saying 1 times 5. That is, this times this became this. What about this 6? It is as if this was gotten by saying 3 times 2. That is 3 times 2. While 5 was gotten by saying 1 times 5. What about this 15? It is as if it was gotten from this operation by saying 3 times 5. That is, this 15 is equal to 3 times 5. Is this a coincidence? To check if this is a coincidence, we need one more example to be sure that this is not a coincidence. Please permit me to choose another number operation to observe something from, so we find out whether what we are observing here is just by chance or not. Please follow up. Now see that second example. I want to add 2 over 3 to 1 over 4 using that same style, that same line of reasoning as we had before. 2 over 3 and 1 over 4 do not possess the same denominator, but one of the common multiples to 3 and 4 is 12. I want to upgrade this 3 to 12 and upgrade this 4 to 12. So how do I make 2 over 3 become something over 12? And how do I make this 1 over 4 become something over 12? Please watch. What can I multiply 3 with to make it become 12? It is by 4. That means 4 multiplies this 3 and multiplies this 2. So when 2 multiplies 4, it is 8. When 3 multiplies 4, it is 12. That means that 2 over 3 is the same thing as 8 over 12. The two fractions are equivalent. I hope what I'm saying is clear. All right, then 1 over 4 will become something over 12. That means this 4 has to be pushed up to 12. I hope you know how 12 was chosen. 12 is one of the common multiples of 3 and 4. They may have other common multiples, but the smallest, the first very common multiple that 3 and 4 will have when outlined is 12. So we make use of 12. Therefore, that is how this 4 has to be pushed, or why this 4 has to be pushed up to 12. What multiplies this 4 to make it become 12? It is 3. Therefore, that 3 chosen should multiply up and down. If I multiply up by 3, that is 1 times 3, I get this 3. 4 times 3 is this 12. Therefore, 1 over 4 is the same thing as saying 3 over 12. So far, this fraction has become this, and this has become this. Adding these two is the same thing as adding these two, but this is easier because these two don't have the same denominator, but these two possess the same denominator. How do we add this? Recalling the formula for adding or subtracting two fractions that possess the same denominator, what we do is to add this 8 to 3. Please, if you pick 8 out of 12 and somebody picks 3 out of the same 12, it will be easy enough to add 8 to 3 to become 11. That means altogether 11 over 12 is the answer. But how do we get 11 over 12? It is by adding this 8 to 3. That takes us to 8 plus 3 all over 12. Therefore, the summary is that 2 over 3 plus 1 over 4, which is here, is given as 8 plus 3 over 12. Therefore, this is summary of the process. Now, let us check whether the same thing we observed in the former case is applicable here, so that at the end, we now determine or conclude that what we saw before is a coincidence or not. Follow me as I make observations from this second conclusion. Okay, let us make another kind of observation from this line of action. Don't forget that after we added 2 over 3 to 1 over 4, what we got was 8 plus 3 all over 12, which, when written in the simpler form, will be equal to 11 over 12. All right, don't forget my observations in the first instance. Let us do similar observations in this second one. As a reminder, in the first one I said, could it be that this 5 is gotten by saying 1 times 5? Could it be also that this 6 was gotten by saying 3 times 2? See it here. Could it be also that this 15 was gotten by saying 3 times 5? See it here. Now, with this reminder, let's have it fresh in our minds as we look at the second case. Let us make similar observations. Let us check whether what happened here is what happened in the case of 8, 3, and 12. Could it be that this 8 was gotten by saying 2 times 4? I think it is the same thing happening there. All right, let's not conclude yet until we are through with all the 3, that is 8, 3, and 12. What about this 3? What could have happened? Could it be that this 3 is also gotten by saying 3 times 1? Just like this 6 was gotten by saying 3 times 2. Okay, what about 12? Could it be that this 12 was gotten by saying 3 times 4? The same way we reasoned that this 15 could have been gotten by saying 3 times 5 in this case. If you watch this line of observation and these two, that is consistency. The same observation holds for both of them. What if we repeat this a number of times, using both addition and subtraction? Do you think that the same thing is going to come as consistent observation? Certainly, I have done that personally, and I saw that no matter how many times we repeat this, that this observation is always consistent. This consistency is the law of adding and subtracting fractions involving different denominators. Don't forget that I said that whether it is addition or subtraction, this observation is always valid and consistent. That uniformity of result is what we're going to write down as the law for subtracting and adding fractions that possess different denominators. What law could that be? Please follow me as I write the law for adding and subtracting fractions that possess different denominators. And here comes the law for adding and subtracting fractions, two fractions, which contain different denominators. See it here. A over B plus or minus C over D is equal to AD plus or minus BC over BD. Let me use one of these two cases and compare the number operation and the result with this law. This law is just a summary or a conclusion drawn from these operations carried out with constants. Let it be that it is this one we are using to make this conclusion, though this is also used to make the conclusion. Let me just use this to make this conclusion. Let this 1 be A, let this 3 be B. Plus is what is here, but whether it is plus or minus, it is valid. That is why I wrote here plus or minus. Then 2 is this C, 5 is this D. That does not mean that in every case A is 1 and B is 3 and C is 2 and D is 5. This is just a case in point. In other cases that you will find later, A can become any number, B can become any number. The same thing applicable to C and D. All right. Since we learned that this 5 was obtained by saying 1 times 5. 1 times 5 is something as saying A times D. See it here, AD. Which means this 5 is AD. AD means A times D. Okay, now this plus is used here because plus is what is currently being used. But in cases you're going to see in the future, like I said earlier, you might also meet subtraction. The proof so far given did not feature subtraction, but I challenge you to choose other fractions that may have subtraction and carry out the same thing. You will see that the conclusions drawn here are valid. Let's go on, please. Also, just as this 6 is the same thing as saying 3 times 2, which means 3 times 2 gave us this 6 here. What it means is that this BC is gotten by saying B times C. So B times C is equal to BC. The same thing, the same way we have 3 times 2 is this 6. I just hope that what I'm saying here is making sense to you. All right, what about this BD? Just as this 15 was gotten by saying 3 times 5, this BD is gotten by saying B times D. This minus is not between B and D. The minus here is to show that the sign between them could be plus or minus. Please don't be confused. So B times D is this BD. Therefore, following how this number operation was evaluated, this law has become valid because of consistency. Let me recast this law in a way that will make you remember it at all times. And here it comes in a border form. In this border form, I believe it is going to serve as a powerful reminder. Again, the formula for adding and subtracting fractions that possess different denominators, mainly when there are two fractions, is A over B plus or minus C over D is equal to AD plus or minus BC over BD. Let me present some examples of number operations involving addition and subtraction of fractions that possess different denominators using this formula. Please watch. And now let us see examples. 3 examples of addition and subtraction of 2 fractions with this formula. 2 over 3 plus 1 over 5. In this case, our A is 2, our B is 3, our C is 1, our D is 5. How do we get what is next? Get AD, get BC, and get BD. What is our AD? Please, this is the problem, and this is solution. Likewise, this is the problem, and this is solution. And this is the final solution after simplifying the solution. Let's see how we used this solution to get this solution. What's our AD? Having known what our A, B, C, and D are. So our AD will be 2 times 5. See it here, 10. Is it plus or minus we're going to make use of? It is plus because plus is between them. What is our BC? Our BC is 3 times 1. That is B times C means 3 times 1. That is it. And that will give us 3. Then what about our BD? Our BD will be this B times D. That will be 3 times 5. The result is 15. Therefore, 2 over 3 plus 1 over 5 is equal to 10 plus 3 over 15. So eventually the answer is equal to 13 over 15. The next example is 3 over 5 minus 1 over 7. Our A in this case is 3, our B is 5, our C is 1, our D is 7. And what we're going to make use of is this subtraction. Plus will not come in. Why? Because the case in point says minus. Therefore, the next thing we do is to recognize the fact that this is a problem and this is solution. Likewise, this is a problem and what is here is solution in line with this thing given to us. So next, our AD is going to be 3 times 7. That is AD. A times D will give us this. Likewise, 3 times 7 will give us 21. Next is BC. BC is B times C. That will give us 5 minus 1. That will give us this 5 here. And minus is between them. That is why it is this point. Next is this BD. That is B times D, giving us 5 times 7. The thing is 35. I hope what is happening here is clear to you. Now let's make progress. 21 minus 5 is 16. And 16 over this 35 is the correct answer. Can this go down to lowest term? No. The answer therefore remains 16 over 35. The third example goes this way. 4 over 5 plus 1 over 2. Our A is 4, our B is 5, our C is 1, our D is 2. And what we're using of these two signs is plus. Therefore, This is a problem and this is solution. Likewise, this is a problem and this is solution. Now get AD. What is AD? AD is A times D. Correspondingly, that is 4 times 2. That is this 8. What about this BC? BC is B times C. That corresponds to 5 times 1. Say 5 here. And plus is here. That is why the plus is here. Next will be this BD. BD is gotten by saying B times this D. That will be 5 times this 2. That will be equal to 10. So this is a problem and this is solution. To get the last answer, we simplify this solution. 8 plus 5 is equal to 13 and then over 10. Therefore, 13 over 10 is the answer. 13 over 10 is the answer, and this is an improper fraction. In fact, this is not a fraction, it is a pure division. And if we carry out division, we are going to get one whole number. The remaining 3, the 10% will still divide it. That takes us to a mixed number, which is one whole number, 3 over 12. At this point, I believe that you will be following, and you are supposed to test if you have been following. Please watch out for an exercise. And now here comes the checkpoint. It says, using the equation A over B plus or minus C over D is equal to AD plus or minus BC over BD. Solve the following number operations. There are only 4 in number. The first, 4 over 7 plus 2 over 5. Number 2, 3 over 5 minus 1 over 8. Number 3, 2 over 5 minus 1 over 2. The last one, that's number 4, 4 over 9 plus 3 over 4. Notice that all of these number operations involve only 2 fractions. Now, let us attempt finding a second method of adding and subtracting fractions. This time around, let us see whether we can extend the formula to adding and subtracting fractions that are not restricted to only 2 fractions. Please follow me as I try to get a second formula for adding and subtracting fractions. All right, with the same set of fractions which we used to before, let us try to get a formula, second formula for adding and subtracting fractions, especially those fractions that may be more than 2 in number. In the meantime, let us go back to our former fractions, 1 over 3 plus 2 over 5. Recall that this was one of the results we got earlier, which also became this, and this. That means that in solving this, we got how many results? 1, 2, 3, 4, 5 results. That means that in solving this, we got 5 results. Each of these 5 results is correct. We can equate this number operation to any of the 5 results. If that happens, nothing bad has happened because this number operation results in any of these 5. Permit me to equate this number operation to this. Let that happen, please. And here it comes. This number operation is now equated to this result. And we can choose to equate it further to this. This is what is summarized in this line of operation. So 1 over 3 plus 2 over 5 is equal to 1 times 5 over 15 plus 2 times 3 over 15, which is equal to 5 plus 6 over 15. Let us make some observations which will connect some or all of these 3 portions of this line of action. First, focus on this 5. Don't forget that before, we also stated using another observation how this 5 could have been got, how this 6 could have been got, and how 15 could have been got. This time around, we're going to look at another way that this 5 could have been got and how another way this 6 could have been got. We know that this 15 is actually one of the common multiples of 3 and 5. Any other common multiple can serve. We shall get back to it as to which common multiple is the best to be used in evaluating addition and subtraction of fractions of this sort. Let's continue. Let us check another way this 5 can be gotten. Could it be that this 5 is gotten like this? Please reflect on it. Could it be that this 5 is gotten simply by saying, when this 15 is here, 15 is here, choose one, divide it by this 3, and the remainder, the result, times 1. One of these two, that is, divide 15 by 3. The result times 1. See it here. 15 divided by 3. Whatever you get times 1. The 1 is this numerator. If 1 had not been what is here, then whatever is here would have still multiplied this division. But because 1 is what is there, 1 is what is here. When 3 divides 15, the answer is 5. 5 times 1 is equal to 5, which is this 5. So this is my observation as to how this 5 could have come into being. Don't forget that this is the second observation I am making about adding and subtracting fractions. And all along, we'll be using this 1/3 plus 2/5. What about this 6 here? How would this 6 have come into existence? Considering the former portions of this line of operation, it is possible that this 6 was obtained by dividing this 15, which is the common denominator, or you can also call it common multiple. Whichever case, 15 is common. And so, could it be that this 6 was obtained by dividing this common denominator by this 5? If we get the result, we multiply the result by 2. Let's check if it is like that. 15 is common multiple. We divide it by this 5. The 5 is this 5. After we divide 15 by 5, the result is 3. That means that this bracket will have 3 as the number inside it. So 3 times 2 is equal to this 6. This observation is correct, but we don't know if it is consistent. To be sure it is consistent, let us choose 1 or 2 more examples of number operations that have to do with addition and subtraction of fractions that possess different denominators. Anyway, let me present the same addition of these 2 fractions using a different number, a different common multiple. Don't forget that 3 and 5 still also possess 30 as their common multiple. Let me represent or recast this number operation using 30 as their common denominator. Please follow me as that happens. And that example is here. The same 1/3 plus 2/5 is done in a different way. 3 and 5, apart from having 15 as their common multiple, also have 30 as their common multiple. So I'll choose 30 as the common multiple of 3 and 5 in solving it in this way. With the same pattern of reasoning, we have that 1 over 3 plus 2 over 5 is equal to 1 times 10. That is, I'm converting this 1 over 3 to something over 30, just like I converted 1 over 3 to something over 15. So when I chose 15 as their common multiple, I had to upgrade this to become something over 15, which happens to be this. And also upgrade this 2 over 5 to something over 15, which at last became this. Likewise, since 3 and 5 can still possess other common multiples apart from 15, I choose to use 30 as the common multiple for 3 and 5 to repeat the same process here. I want now to convert this 1 over 3 to a kind of fraction possessing something over 30. So how do I convert this 3 to 30 first? It is by multiplying it by 10, which means I multiply up and down by 10. See it happening here. Therefore, this 1 over 3 is being upgraded to become 1 times 10 over 3 times 10. That will give us 10 over 30. Likewise, this 2 over 5 is being upgraded to something over 30. How do I make this 5 become 30? It is by multiplying it by 6. That means that 6 must multiply up and down. See where 6 is multiplying up and down to give us 2 times 6 over 5 times 6. That gave rise to 12 over 30. Therefore, this has become this, the 2 being equivalent, while this has become this, the 2 also being equivalent. At this point, because 10 over 30 plus 12 over 30 is addition of 2 fractions that possess the same denominator, adding them is the same thing as adding these 2. Let's make progress. How do we add them? 10 picked out of 30 added to 12 picked out of the same 30 will give us 22 picked out of 30. But before then, 22 was just gotten by putting 12 and 10 together. That will be 10 plus 12 all over this 30. And that gave rise to 22 over 30. This is the answer, but it has to be broken down or reduced to its lowest term. If that is done, that will give us this 11 over 15, the same answer we got earlier. So whether we pick 30 as the common multiple of 3 and 5, or 15 as common multiple of 3 and 5, the result has come to be the same thing, 11 over 15. What else do you think will serve as common multiples of 3 and 5? 45 will be. Other higher numbers will also be common multiples. That means that another kind of process can be repeated, adding 1 over 3 to 2 over 5 using 45 as the common multiple. Whichever common multiple is used, this fact stands out in all of them. Now, like before, permit me to equate this number operation to one of these results or 2 of them. I want to equate this number operation to this and then this. See it here. 1 over 3 plus 2 over 5 is equal to 1 times 10 over 30, which is this, plus 2 times 6 over 30. See it here. And that is equal to 10 plus 12 over 30. See it here. That means that this is equal to this or this. This line of action will help me to make observations similar to the ones I made in the former line of operation. Again, in line with what I had made before, I want to see how I can get conclusion as to how this 10 was gotten and how this 12 was gotten. As a reminder, with the first one, I said that this 5 could have been gotten by saying, let this 3 divide 15, which is the common multiple. See it happening here. When the result is gotten, multiply it by this numerator, which is 1. See it here. Likewise, this 6 could have been gotten by saying, let this 5 divide this common multiple. Not both of them, but one of them as common multiple. So when 5 divides 15, see it happening here, 5 dividing 15. The result of that times this 2, which is numerator. So when 5 divides 15, the result is 3. 3 times 2 is this 6. When 3 divides 15, it is 5. 5 times this 1 is 5. Let's carry the same idea down to this place to check if it is consistent with this line of operation. Now I want to use similar reasoning to check whether the same thing is applicable to how this 10 was gotten and how this 12 was gotten. Don't forget that we are carrying number operations, and this is supposed to be a numerical experiment that will lead us to creating a formula, a different formula for adding and subtracting fractions, mainly those that possess different denominators. It does not mean that if you apply this to those fractions that possess the same denominators that failure will come. No, we are simply saying that this is especially going to be applied in addition and subtraction of fractions, 2 or more fractions that possess different denominators. Let's go on, please. How was this 10 gotten? I say again, perhaps it was when 3 divided 30, which is their common multiple. See 3 dividing the 30, the result times this 1 here. Please, when 3 divides 30, what is the result? It is 10. 10 times 1 is that 10. That's how this 10 was gotten. So this explains how this 10 was gotten, meaning this 10, which is this 10, was gotten like this. Is it consistent? Let's check 12. How was this 12 gotten? Perhaps let 5 divide this 30. See 5 dividing the 30. When that happens, the result times 2. When 5 divides 30, the result is 6. Then 6 times 2 will give us this 12 here. Based on that, if we watch this observation and this one, that is just one thing we can say. That is consistency. Even if you choose many other examples in like manner, you will see that these observations are valid. And even if you choose to carry out subtraction, these observations are still valid. That I have tested. It is that consistency that will lead me to writing a second formula for adding and subtracting fractions, 2 or more fractions that possess especially different denominators. Please watch out for the formula. And here is the formula for adding and subtracting fractions. A different method from the first one. It says A over B plus or minus C over D is equal to A bracket M over B plus or minus C bracket M over D all over M. You might wonder what this M is. It is just common multiple. In this first line of operation, we used 15 as their common multiple. That means that in this first line of operation, M was 15, just like you can see. And in second line of operation, the M was 30, as you can see. So 15 as the M, the first line of operation, and 30, the common multiple for second line of operation. You can repeat the same thing with M being 45 or even higher. In the meantime, I just believe that you have known what this M stands for. All right, so this is second formula and more encompassing formula for adding and subtracting fractions. The formula is just very clear and gives us a clear direction. If you want to add two or more fractions, let us do it two fractions because they are simpler to handle. A over B plus or minus C over D. This is a problem, and this is how to solve it. It simply says, choose a common multiple for these two denominators, or more in the case of more fractions being added or subtracted. Let that common multiple be called M. Okay? Let that common multiple be called M. First, divide that common multiple by this B. See where B is dividing it. When B divides the common multiple, the result you got times this A. See it here. Let that same common multiple be divided by this D. See where D is dividing that common multiple, that is D dividing this M. The result you've gotten from there times this C. See it here. So the summary is A bracket M over B. Then the other one is C bracket M over D. After everything altogether over this M. This summarizes what actually happened from these two lines of operations. Let me rewrite this law in a bolder form as a reminder. And here is that same formula in a bolder form as a reminder. A over B plus minus C over D is the problem, and this is how to solve it. At this point, let me remind you that any of the common multiples of these denominators can serve as M, but it is always better to choose the lowest common multiple. That is why in practice, people look for LCM of this B and D. They say, find the LCM of the denominators. Divide that LCM each time by the numerator, by the denominators. And when the answer is gotten each time, multiply the result by the corresponding numerator. This is what is summarized here. All right, let us see some examples of addition and subtraction of fractions, sometimes two or more fractions that will be dealt with using this formula. Please follow through. And now let us see three examples of application of this formula. The first is 3 over 8 plus 2 over 5. Our A is 3, our B is 8, our C is 2, our D is 5. What then is our M? That is the common multiple, especially the lowest common multiple. The lowest common multiple to 8 and 5 is 40. So our M is 40. See it here. In the end, let this 8 divide 40. See it happening here. And the result times 3. See it happening. So when 8 divides 40, it is 5. 5 times 3 is 15. I hope you now know how this 15 was gotten. Next, let this 5 divide the common multiple. That is, let 5 divide 40. See where 5 is dividing 40. When 5 divides 40, the result is 8. When you get the result, times this 2. That is times this 2. So 8 times 2 is this 16. And 40 is still here. That means that this produced 15 and this produced 16. And the 2 must be added. After being added, then we'll have over 40. So 15 plus 16 over 40 is the same thing as saying 31 over 40. And that is the correct answer. Whether I apply that first formula or this one, the result is the same, 31 over 14. Let us look at a case that contains more than 2 fractions. This is an advantage this formula has over the first one. The first one is a quick method, a quick way of finding out sum or difference of only 2 fractions. But in this case, this formula has been tested to work whether we are adding 2 or more fractions. Example 2 is just going to highlight the authenticity. Now let's have it. 7 over 10 plus 1 over 3 plus 5 over 6. Now, what is our A? Our A is 7, our B is 10, our C is 1, our D is 3. We can also have something like E over F, where E is 5 and F is this 6, and so on and so forth. It thinks that we have 2 here doesn't mean that 2 alone must be involved. Remember, that has been tested to be correct. Now, what is the M? The M is the common multiple. The common multiple can be any of the multiples common to 10, 3, and 6. The first and the lowest common multiple to 10, 3, and 6 is 30. Therefore, with this formula in view, let 10 divide that common multiple and the result times 7. Let this 3 divide that common multiple and the result times 1. Let 6 divide that common multiple and the result times 5. See where it is playing out here. That is 10 dividing 30 is 3. 3 times this 7 is 21. And then you have this 3, which is this 3, dividing this 30. The answer is 10. 10 times 1 is this 10 here. Then this 5, dividing the common multiple, this 6 dividing common multiple. This is 6 dividing this 30. The result is equal to 5. 5 times this 5 is this 25. Now, I believe you know why we got 21 here, 10 here, and 25. And because what we have in every portion here is sign of addition, we have it all through as operation to be carried out with numerators. So we now have 21 plus 10 plus 25. 21 plus 10 plus 25 will give us 56. Now at this point we have 56 over 30. All right, please, this is not the last answer, but it is close to what is last. Please reduce this to something simpler, and later, because what they're going to get is not a fraction, convert the thing to a mixed fraction. I believe you can do that. All right, the example number 3 highlights the importance of the fact that apart from addition, we also use this formula for subtraction of fractions. We have 4 over 5 minus 2 over 7. And then what is next? Our A is 4, our B is 5, our C is 2, our D is 7. What is our M? Our M is going to be the common multiple of 5 and 7. They have different common multiples, but the lowest here is 35. So let's use it. Let this 5 divide it, the result times 4. Let this 7 divide it. Divide what? The common multiple, and the result times 2. See it playing out here. So when 5 divides 35, the answer is 7. 7 times 4 is 28. See it here. And then next is when 7 divides 35, the result is 5. 5 times this 2 is 10. See it here. So leading us to 28 minus 10 all over 35. Please, 28 minus 10 is 18, then over 35. And this is the answer because we can't reduce this 18 over 35 to lowest term. All right, at this point, check if you have been following and then How do you do it? Look out for an exercise. And here comes the checkpoint. It says, using the relation A over B plus or minus C over D is equal to A bracket M over B plus or minus C bracket M over D all over M. Simplify the following operations. The first is 3 over 5 plus 1 over 6. Second, that's number 2, we have 2 over 3 plus 3 over 4 plus 1 over 8. The third question is 4 over 7 minus 2 over 3. By the time you come to solving this number 3, you may realize that at the end, the answers we get are not always to be positive. Here, you will see an answer that is not positive at the end. If you get a positive result, you think that something is wrong with the process that led to your answer. Be careful as you solve this, because in the course of giving you examples, I did not present a case that led to anything negative. So this number 3 will just be a case of that kind. Then the fourth one is 7 over 8 minus 1 over 5 minus 1 over 10.